This talk is about parasitic torques and noise in the induction motor. It's a personal view. Although it is generously hosted by JSOL, it does not represent JSOL in any way. These videos may seem rather low-key. That's because I'm trying to encourage calm reflection of rather abstract topics, even though this is a very practical subject. I've used this chart many times before, but all we need to do here is to fix our minds on where we are in the family of electric machines. We're talking about the induction motor, and in particular the line start induction motor. These motors are extremely common, and they convert something like half the electricity that is generated in pumps, fans, compressors, and hundreds of other applications. The line start motor has no electronics. It starts and runs by switching on to the mains power supply directly at 50 or 60 Hertz. Here's an example kindly provided by Motivity Limited in Galashiels, Scotland. We can see only the stator. It's a two-pole, single-phase capacitor motor. And here is another example, kindly supplied by MCC Sekop in Germany. It's a refrigerator compressor motor, again two-pole, capacitor start. And here we can see also the cage-type rotor with cast aluminium conductors. Although both these motors are single-phase motors, everything in this webinar relates to motors of any number of phases. Next we see the speed-torque characteristic, actually two versions of it, one on the right and one on the left. Since these are line start motors, they start from standstill and they must accelerate under their own asynchronous torque all the way up past the breakdown point to a speed near synchronous speed where they're supposed to settle. The precise operating speed depends on the intersection of the speed-torque curve of the load and that of the motor. There is, of course, no standard load curve, and we're not showing a load curve here, but we can say that fans and blowers have a torque which increases more or less quadratically with speed, while compressors and conveyors tend to have a flatter curve nearer to a constant torque characteristic. Now each one of these curves has an irregularity at a fairly low speed. The one on the left is called an asynchronous torque dip, while the one on the right is called a synchronous torque dip. I'm not sure if dip is the best term, but it's the term used by some venerable authors, and we'll use it here. Other terms which have been used include cusp and hook. In either case, we can see that if the load curve intersects the motor characteristic in the region of the dip, there's a danger that the motor will hang up and not accelerate through this region. Obviously, that is unsatisfactory. This condition is called crawling or cogging. I'm not sure of the origin of these terms. I tend to associate crawling with the asynchronous torque dip and cogging with the synchronous torque dip. Certainly, cogging suggests the phenomenon which causes the synchronous torque dip, as we will see. Either way, when the motor is crawling or cogging, it makes a very unpleasant noise, and even if it gets through this region, it may still be noisy as it passes through. To extend this, there is a possibility of noise coming from several different sources, and so the subject of parasitic torques or torque irregularities is closely bound up with the subject of noise. The subject of noise is actually a good place to start a study of torque irregularities. Historically, the analysis of both aspects developed on parallel lines, and rules of thumb were developed to counteract both the noise and the risk of starting difficulties. It may be helpful, indeed I would say it's very helpful, to begin with some idea of mechanical imperfections which might cause a noise problem. There are many of these, but one that is relevant here is eccentricity. There are many definitions of eccentricity, but here we see a clear definition of three main types: static eccentricity, dynamic eccentricity, and this one on the right where the shaft is not parallel to the stator axis. This diagram was presented by Professor Akiyama and Osamu Sugiura at the 1992 IEEE IAS conference in a paper on what they call the 2SF beat phenomenon in induction motors. By a program of theory and experiment, they showed that the middle one, dynamic eccentricity, could result in a beating noise at twice the slip frequency. In this mode, the rotor is pulled over to one side as if by an unbalanced magnetic pull or radial force, and it may whirl around the shaft center line. In the next slide we can see why this is such a good introduction to the subject. On the right hand side we see the effect of a radial force resulting from two rotating flux waves whose pole number differs by 2. At the bottom is a construction showing the typical shape of this force field. Of course it is idealized, but the main point is the resultant unbalanced pull in one direction. Depending on the origins of the field, the resultant force can rotate in either direction, and it can even be stationary. Pairs of flux waves differing by 2 in their pole numbers may arise in several ways, but before we investigate further, let us pause to look at the other two diagrams in this slide. At the top left is the situation where we have two flux waves having the same pole number but rotating in opposite directions. This is the classic case of the so-called pulsating torque in the single-phase motor or in an unbalanced polyphase motor. It is an alternating torque at double the line frequency, and in the single-phase motor it is typically of the same order of magnitude as the rated running torque, so it can be very large. Of course it vanishes if the motor is operated as a balanced two-phase motor, but this condition is extremely rare. The problem with this oscillatory torque is that it is transmitted directly to the mountings, which provide a path for the transmission of noise. For this reason, single-phase motors are often provided with compliant or resilient bearing mountings, springs, to attenuate the transmitted torque oscillation. Then at the bottom left we have the case of two flux waves differing in pole number by 4. The tendency here is for the force field to ovalize the rotor or stator, or both of them, into an elliptical shape. We might expect that elliptical deformation must be very small in such a rigid structure as a well-made electric motor, but it's all a question of resonances, and ovalization is one of the common low-order modes of vibration of ring-shaped structures like the stator. Remember that the deflection needed to produce an audible noise is very small. So we can approach the problem of noise and torque irregularities by investigating the harmonic fields in the motor, and the place to start is with the stator MMF harmonics, because these can cause parasitic torques even with a perfectly smooth air gap. So here we see in fact two alternative concentric windings for a single-phase motor. They're both concentric windings with a nested set of coils, all having the same axis of symmetry, but different spans and different numbers of turns. The one on the left is a practical winding with 5 coils and turns distributed in the ratio 3:3:2:2:2, as we can see in the small bar chart in the middle. The one on the right is a hypothetical winding with 6 coils, in which the turns are distributed sinusoidally. The numbers of turns in these coils are not integers, and of course this is impossible. But the point of this winding is to act as a theoretical reference as near as possible to a pure sign-distributed winding, which we hope will have no MMF harmonics. By the way, at the top we can see the fundamental winding factors, and it turns out that the winding factor of the practical winding is almost as good or almost as bad as that of the sign-distributed winding. Both of them are rather low, but we're digressing. Next, the way we analyze the winding harmonics is to take one coil at a time and postulate its MMF wave around the air gap. This is a stepped wave where the steps are equal to the ampere conductors in one coil side. Since there are 2 coil sides with equal numbers of ampere conductors of opposite sign, the MMF goes up and then it comes down. The width of this rectangular section is equal to the coil span. We can see that the wave is not symmetrical, and it will contain even as well as odd harmonics. But we ignore the even harmonics on the assumption that the winding is going to be balanced between its north and south poles. But we should take note of the fact that if this balance is not perfect, the winding will have even order MMF harmonics, and it will cause even order flux harmonics, and these will tend to flow in return paths which include the shaft and bearings, and which will be a source of trouble, including noise. Any oscillatory axial forces can cause the rotor to vibrate in the axial direction, which is not good for the bearings. Now, the method of resolving the rectangular MMF wave into harmonics is Fourier's series. And I should mention here the vital importance of using Fourier's series and not the FFT. The waveforms are periodic, and although there are special cases where the discrete Fourier transform can be identified with some of the coefficients, the FFT is the wrong tool for this work, and we should always use the Fourier series. Otherwise we'll run the risk of departing from the classical theory and coming up with the wrong winding factors. So here is a standard example of the Fourier analysis of a square wave into its harmonic components. The fundamental, the third, the fifth, and the seventh higher order components are not shown. The idea, of course, is that if we add all the harmonics together, we will recover the original square wave. Now this diagram shows the MMF distribution for the 2 windings. We're showing only half a pole for each winding. The practical 5-coil winding on the left, and the sign-distributed 6-coil winding on the right. At the bottom we see all the coils, the actual coils, the slot fill shading and the coil side markers are scaled to the number of turns in each slot. We also see the histogram of the ampere conductors in each slot, and the integral of this distribution is the stepped MMF wave in red. Then by Fourier's series we extract the fundamentals of the MMF waveforms. These are plotted in red dashed lines, and the whole diagram is scaled so that we get the same fundamental MMF sine wave for both windings. Finally, we have the green sine waves representing the fundamental MMF that we would get if all the conductors were concentrated or bunched into a single full pitch coil. That, of course, is not possible in this case because we have a tooth in the way on either side. But nevertheless, this is the reference or benchmark on which the winding factor is calculated. Now, if we look at all the harmonic coefficients using Fourier series, we get a chart like this one for the practical winding and this one for the sign distributed 6-coil winding. It's clear that with the sign distribution we have eliminated all the low order harmonics, but these two, the 23rd and 25th, have the same winding factor as the fundamental. These are called the step harmonics. Sometimes they're called the slot harmonics, and their order is the number of slots plus or minus the number of pole pairs. Although their effect in producing flux harmonics is inversely proportional to their harmonic order, as well as the winding factor, they can be troublesome, and the point to note is that they always have the same winding factor as the fundamental, and so they cannot be eliminated by the choice of winding distribution. Going back to the practical winding, we can see some small low-order harmonics. It's good that they're small, because each one of these, in principle, acts like a parasitic induction motor on the same shaft as the fundamental, and produces an asynchronous speed-torque characteristic having almost the same shape as the fundamental one, but centered on its own synchronous speed. This synchronous speed can be forwards or backwards, but it's always inversely proportional to the harmonic order. So, for example, in this figure we see an asynchronous parasitic torque at 1/7 of the fundamental synchronous speed, rotating in the forward direction. It's caused purely by the 7th space harmonic of the stator MMF. This would be the one to watch out for in a 3-phase motor. But in a single-phase motor, it's the 3rd harmonic that's most likely to cause this parasitic torque. Next, we return to the search for harmonic flux waves with a pole number difference of 2. Recall that this was identified as a source of noise rather than a parasitic torque, and we took a long diversion into the harmonic analysis of windings. To help in navigating the rather complex interactions that can occur, I use a spreadsheet which contains most of the known tests for undesirable conditions. Of course, I mean known to me. There may be others. Here is an example for a 24-slot, 2-pole motor with 17 rotor slots. Now, the place to start is this large table at the top. And I'm afraid we have to contend with another theoretical complication at this point. If the winding is balanced and contains only odd-order MMF harmonics, we are never going to find two waves differing in pole number by 2. For example, the 23rd and 25th differ in pole number by 4, because they differ in pole pair number by 2. To find a difference of 2, we have to consider the variations in permeance caused by the slotting, and in particular we're looking for the interaction of the stator MMF harmonics with these permeance variations. As the rotor rotates past the stator, it presents a varying permeance because of the slotting on both sides of the air gap, and this results in additional harmonics in the flux wave. This approach dates back to Hildebrand in 1930. Hildebrand identified 6 sources of permeance harmonics relevant to this search, and here we can see them listed together with their harmonic orders. P is the number of pole pairs, ZS is the number of stator slots, and ZR is the number of rotor slots. DZ is the difference between the number of stator slots and the number of rotor slots, and this one is not so intuitive. If the table is blank, it means there is no pair of flux waves with a pole number difference of 2. But here, for example, with 17 rotor slots, we can see no fewer than 8 cases which give rise to the pole number difference of 2. If we look at the 17th MMF harmonic, it has 17 pole pairs. And then this permeance harmonic at P plus ZR has 1 plus 17 equals 18 pole pairs. So the difference in pole pairs is 1 and the difference in poles is 2, and it shows up in bold red type. The 17th stator MMF harmonic also interacts with a permeance harmonic at P minus ZR minus 16, and the bold red type shows a difference of 1 pole pair again. The plus or minus sign indicates the direction of rotation of the resulting two-pole flux wave. It turns out that we get these two-pole differences somewhere in the chart whenever we have an odd number of rotor slots. If we choose an even number, this table becomes blank, and apparently we're safe. But oh no, it's not as simple as that. There are dozens of other rules which have to be considered, and you can see some of them here. I'm not going into the other rules here. It becomes too complicated for a short video like this one. But this is quite a good point at which to consider skew. The early workers in this field included Hildebrand and others who are very well documented in the English, American, and especially the German literature, and they considered skew from an early stage. The general principle was to skew the rotor bars by 2 pole pitches of the harmonic that is causing the problem. So here we have a representation of the harmonic flux waves along the length of the machine. On the left, this one has no skew, and there will be a harmonic EMF and a torque with no attenuation along the length. With a skew of 2 harmonic pole pitches, the harmonic EMF and torque in the 2 halves of the conductor cancel out. That's the idea of using 2 harmonic pole pitches. A skew of only 1 harmonic pole pitch is the worst possible, because the EMF and torque in the 2 halves are additive. There might only be a small difference between 1 harmonic pole pitch and 2 harmonic pole pitches, indicating that the amount of skew is quite critical. And for some reasons, 4 harmonic pole pitches is suggested as being the best one. Now, a difficulty, just one difficulty with this, is that there is a multiplicity of harmonic flux waves, and it may not be easy to pick out the most troublesome one. There may be more than one that is troublesome, and what do we do then? This indicates one traditional strategy, which is to choose the slot combination very carefully, so that the only troublesome harmonic flux waves are the ones associated with the step harmonics, in this case the 23rd and the 25th, and to use skew to quell those. 2 pole pitches of the 23rd harmonic would be 15.65 degrees, which is 1.04 stator slot pitches, and 4 pole pitches would be 31.3 degrees. We would certainly see that on the rotor, and sometimes we do see it. Now finally, I would like to focus on a synchronous torque dip, or at least the cause of it. Here we see a combination of 24 stator slots and 26 rotor slots. It breaks more than one of the rules if you were watching carefully, and we'll see why in just a moment. In the left-hand diagram, the rotor is in such a position where we have perfect alignment between two pairs of stator and rotor teeth. Stator tooth number 1 at 0 degrees and number 13 at 180 degrees. In the orthogonal axis, we have an unaligned condition at tooth number 7 at 90 degrees and tooth number 19 at minus 90 degrees. This slide shows what we mean by aligned and unaligned. The overlap between a stator tooth and a rotor tooth is maximum in the aligned case, and so is the permeance. In the unaligned case, the permeance is a minimum, and the stator tooth lies midway between two rotor teeth. The result is what is called a detent torque, if we borrow a term from the stepper motor. Any stator MMF aligned with the x-axis will tend to align the rotor, even lock the rotor, in the aligned position. This is exactly the mode of operation of a vernier reluctance motor or slow-speed synchronous AC motor, and it is similar to the operation of stepper motors and switched reluctance motors. In the right-hand diagram, the rotor has rotated forwards by 1/2 a rotor slot pitch, that is 360 divided by 52 or 6.923 degrees. Now the aligned pairs are at plus or minus 90 degrees, while the unaligned pairs are at 0 and 180 degrees. This suggests that in the time taken for the MMF wave, let's say the fundamental MMF wave, to rotate 90 degrees, the rotor advances 6.923 degrees, so it will tend to rotate at 1/13th of the synchronous speed as a synchronous motor. That's the origin of this synchronous cogging torque dip at 1/13th of the synchronous speed. In fact, during the 90-degree rotation of the fundamental MMF wave, there are 6 successive alignments of the adjacent teeth on the stator and rotor, tooth to tooth, tooth to tooth, tooth to tooth, and so on. In the time taken for the MMF wave to move 1 stator slot pitch, the rotor has to advance only the difference of the slot pitches, and this is expressed by the top equation here, which equates these times and produces the ratio of the actual rotor cogging speed to the synchronous speed, nr over ns. So when can this undesirable condition arise? Well, let's look at the pattern of alignments, or the pattern of overlaps between stator and rotor teeth, which are highlighted in black. Going round the air gap, we can see a 2-pole pattern of alignments, really a stepped gradation of alignments, but with a definite 2-pole structure. This is what causes the trouble, and it arises naturally with a difference of 2 in the slot numbers, as expressed by this equation at lower left. However, we can easily imagine a 4-pole or 6-pole pattern of alignments, and so Cron's first rule, this one, can easily be generalized to the difference equal to the number of poles, giving this condition, which is sometimes presented in this form. Slots per pole on the rotor must not equal the slots per pole on the stator plus or minus 1. It's quite scary to go back to the spreadsheet, and I'm not going to do it, because at this point there is an explosion in the number of rules. Not only that, but the rules become blurred. The reasons for them become more and more obscure, and the conditions under which they may be broken multiply until we have a state of considerable confusion. On top of that, our faith in skew is compromised, as it has already been compromised by the multiplicity of harmonics that we have to deal with. The rotor is susceptible to parasitic currents flowing through the laminations, yes, in the axial direction where they interfere with the intended operation of the cage winding. They often bleed current from the bars, and they do this in a patchy way, more in some parts of the rotor than in others. Skewing itself changes the pattern of these so-called parasitic cross-path interbar currents, and on top of that, it modulates the degree of saturation along the length of the machine as well. All of this is very complicated, and I would say it explains why there is so much advanced analysis, even for inverter-fed motors, which do not always have to run up from standstill on the line frequency, but are always operating at low slip, apparently far away from any dips. But for inverter-fed motors, there's another complication, which is the effect of time harmonics in the current and voltage waveforms. Time harmonics. Aren't all harmonics time harmonics? Absolutely not. All the harmonics we've been talking about here are spatial harmonics. We have tacitly assumed that the voltage and current are sinusoidal functions of time, with no harmonics, and we still get the parasitic torques. If on top of that we have time harmonics in the current waveform, it becomes still more complicated. If you would like to see a table of some of the interacting space and time harmonics, you can find them in the Green Book, Chapter 12. The Green Book considers these harmonics only for permanent magnet brushless motors. You won't find anything on induction motors in the Green Book, although it does describe the line start PM motor, which is even more complicated. And that is a sign I've reached the end. Thank you for listening.